Hi folks, this is CEO speaking again. I want to start by thanking you all for watching my videos in 2024. Close your eyes for a second and put your wildest wishes in this wonderful carriage from Lake George, New York. And despite any bumps in the road, let a horse carrying gum in the next year for you and make them true. Cheers, salut, saluti, prost, na zdrowie, dzięki, norok, yamas. And now let's go back to business. What's on the plate for today? What is the relationship between counting in binary and having that information converted in decimal so we can see it on our 7-segment display? Here in the top, I replicated the rudimentary counter from the video 28 made of JK flip-flops. So in the moment I'm going to start counting, the top is going to just follow in binary code 1, 2, because it's 1, 0, 1, 1 is 3, 1, 0, 0 is 4, and so on. So it's just keeping counting, okay? So what then is the problem? Each flip-flop has connected an LED at the output. So we have 4 flip-flops, 2 in each package, so 4 LEDs. But the display has 7 segments, so we need something or somebody able to convert that information from 4 bits right here, from the 4 outputs of the JK flip-flops, onto the 7 LEDs inside the segment, and not randomly, but in such a way that it makes exactly the numbers represented by the combination in binary. Example here is 0, because all these lights are off, and you have to see zeros everywhere. In the moment you have 0, 0, 0, 1, exactly like you are watching on the code right here in binary, it's 0, 0, 0, 1. This is representing the number 1 in our decimal. So this is the number we want to see on the display. So what is this thing? How do we call this kind of circuit, making the conversion between the 4 bits here to the 7 LEDs on the display? These kind of circuits are generically called decoders, but the decoder is a very generic word. What kind of decoders are they? 7-segment display, decoders, and drivers, because sometimes they also amplify a bit the current. So then, apparently all these 3 things, they do the same job, they show the same thing, apparently, because I'm gonna put in evidence some of the differences between the 3 things built here. And by the way, it's an excellent exemplification of the fact that from one output of each of the 4 JK flip-flops, remember the word fan out. I'm energizing at the same time 3 other inputs from each output. One coming here, one here, and one here, from each of the 4. So now take a look. As we start counting, everything looks pretty the same up to here. And now we see the first difference. You can write the number 6 like this or like that. What's making the difference? Why are not they the same? Simply because the packages, these 2 I put my fingers on, they were made by the manufacturer in such a way that this one displays the number 6 like that, and the other one displays the number 6 like that. So this was not my choice, and there is nothing I can do right now to change that situation. is the way the manufacturer chose for this particular package to show the number 6, sorry, like that. And the manufacturer of this package chose the number 6 like that. So then, if I'm going for a second to find out decoders then, they have to be like this one here or that one. They have to be aligned with the type of the display. This one, 7448, and the CMOS counterpart, 4511. They may also be present in other forms like the LS for the 7448 and for the HC format for the 4511. These ones are matching the common cathode displays. But if you use common anode displays, then you have to use 7447 in the TTL. And interesting thing, this is my favorite, 4543 in the CMOS, simply because if I'm using this one, you see here there is the pin number 6 called phase. I can use this one here in two distinctive ways. So I have it over here, bigger. The package 4543 was actually designed to energize liquid crystal displays. But if you won't go over 10 milliamps per output, you can also energize with no problem 7-segment displays. So what do? The key here for any output, the segments A, B, C, D, E, F, and G, having the resistor connected to the appropriate LED of the display, if you attach this particular decoder to the common cathode display, you have to connect the pin 6 called phase to the ground. And if you connect the common anode display, so the anode of the diode you can see is connected to the positive line, then the phase, the same pin number 6, won't be connected anymore to the ground. It's going to be connected to the plus 5 volt. So you see the difference? You can use the same package to energize both kind of displays, common anode or common cathode, but you have to switch the use of the pin number 6 phase to the ground for the common cathode or to the positive line for the common anode. This is why it's my favorite, because I can use this package for both. Okay? So let us return back to our circuit here. What is the point about having a different, let's say, format for the two displays? Again, there's the combinational circuit inside the package, inside the decoder. So when the decoder receives the 4 inputs, the signals coming from the 4 outputs of the flip-flops, it converts these signals into the appropriate number displayed right here. Like 0, 1, 1, 0 is 6. And let's go further. 7, 8, and 9. Obviously, for the 9 is the same issue here. Actually, it's not an issue, it's just a different way to display the number. This one, I can agree with you, it looks nicer, but this one does also the job very well, so it's still showing clearly the number 9, okay? And you can see also the number 9 here. And now I want to put the problem into light. What if I press the button one more time, and instead of 1001, which is 9, I'm gonna have the 1010, which is 10. In order to have the number 10, everybody will understand that we have to have 2 digits, exactly like here. 1, 0, this is 10 in our decimal, okay? So we need 2 digits. But what happens if you give the binary signals to these decoders also on 4 bits, they are still on 4 bits, but the combination in binary overcomes, it goes over the number 9. What's going to happen? This kind of display refuses to show any number if the combination in binary goes bigger than 1001. This one here, it shows a very strange display. It's a kind of C lowercase. And this one here shows the letter A. And now we can start to understand what is the difference between the three. So in order to understand, I'm going to go back to the table I built here for you. And this is going to show the difference. There is a code we call BCD. That code was invented particularly to have the displays on our multimeters, like this one here, gas pump displays, and anywhere you want to see decimal numbers. And how this code is operating. On 4 bits maximum, we have coded all the decimal numbers from 0, 1, 2, 3, up to 9. If you only want to code the numbers 0 and 1, you only need 1 digit. If you want to code the numbers 2 and 3, you need 2 digits, 1, 0, 1, 1. If you want to code the numbers 4, 5, 6, 7, you need 3 digits, 1, 0, 0, and so on. But if you want to code the number 8, 3 digits are not enough, because on 3 digits, the biggest number you can code is 7, okay? So only for the 8 and 9, you still need 4 bits. For that reason, the engineers established a code made on 4 digits. So here for the numbers which are not actually requiring 4, you can put zeros before, because 0 before any number, you won't change the number. So on 4 bits, they code all the numbers from 0 to 9, but they won't recognize any combination which is coding a number bigger than 9. So this is why here you can only see X's everywhere, because these are not recognized. It's exactly what you see here. When combinations bigger than 9 appear, like this is 10, 11, 12, 13, 14, and 15, the decoder, which is attached to the digit, does not recognize the combinations. You have to press it one more time to go back to 0, and then it restarts to recognize all of them up to 9. So any number bigger than 9 won't be recognized, okay? So this is the famous BCD code. What the BCD stands for? It's a decimal number coded here, but it's coded in binary. So binary coded decimal, and you get the acronym BCD. That's it. This is only designed for digits, because on 1 digit, you can only display numbers from 0 to 9. However, some of the manufacturers, like the ones for the TTL circuit 7447, 7448, they decided to show something, because on the display itself, it wasn't possible to show bigger numbers than 9, but they decided to show something though. Just to tell you, these numbers actually, they represent numbers bigger than 9. And here we are. If you take a look, 0, 1, 2, 3, and so on after 9, up to 9, is okay. But when you see that particular symbol, which is a kind of C, and I'm showing it here again, a kind of C lowercase, this is not C. This is actually representing the number 10. Because again, normally for the number 10, you need 2 digits. But on 1 digit, if you see that, is because of the decoder. It was made by the manufacturers to show you that. And when you have the number 11, it's like the same letter C in a mirror, like this. Or you can see it like that for the number 12. And then for 13, and 14, and when you have 15, it's blank. So now another interesting problem is still here. It's still here. You can have a blank display because of different reasons. One reason is the display may simply not be energized. If it is not energized, whatever you do, it doesn't show anything. The second reason it may be blank is because of this. The display may show you the number 15 if the decoder is 74, 47, or 48. The third reason is this one here. The decoder attached to it may not be able to recognize any combination bigger than 9. So between 10 up to 15, the display remains blank. Okay? So there are different reasons why the displays may remain blank. And the fourth reason, if you want it, yes, the display may be effectively defective, which is not the case, okay? Because if I press it one more time, it goes back to 0, okay? So we identified here that this particular decoder attached to the digit, and by the way, the two digits I have here, they're identical. Because I used here the Common Cathode displays. Their code is MAN 6780. And these two are identical. But the reason they don't show the same thing after 9 is not because of them, it's because of the decoders attached to them. So you see the difference now, okay? Then, just as a very simple observation, if you take a look on the numbers bigger than 9, on the 7448, I agree this is the letter C, a lowercase, is the same letter C in the mirror, is a kind of letter C shifted 90 degrees, okay? But here, for these three ones, 12, 13, 14, it's easy to understand what they actually do, because it's like all these three, they are missing one segment right here, right here, right here. This was the letter C lowercase, and the missing segment here is C. So is the missing segment here making them 4, 5, and 6? All of them, they miss the same segment, C. Okay? That was the choice of the manufacturer to represent actually 12, 13, 14. So now very easy to understand what they're actually doing. Okay? And the 15, as you can see, is a blank display. And however, there were some manufacturers which were able to make some displays. This is a very particular one here, DM9368, because if you can see, there's not a standard notation static with 74 with the TTL. It was a particular proprietary notation of the company Fairchild. Okay. You won't find this anymore. It's not available on the market. This one is made by Motorola for the CMOS circuits, and the actual code was 4495. For all their CMOS circuits, Motorola put the number 1 before any actual code of the CMOS. So this is why the code looks a bit longer, because it's 4495 originally, and because it's made by Motorola, it looks like 14495. Okay, this one can still be found. I don't have any right now, but I'm gonna order some. This one can be rarely found, even on Amazon, if not on eBay. And if it is the case, on the 7-segment display, this is what is going to show. It shows the letter A for 10. It shows the lowercase b for 11, uppercase C for 12, D lowercase, E and F 14 and 15. So you see, this particular decoder does a different job than the 7448, because starting 10 to 15, they don't show the same thing. So that one is able to display up to 15. But what is the numerical code which is able to display numbers 0 to 15? If you count, there are 16 combinations. And these 16 combinations, they give us what we call the hexadecimal code. So I put it here again, the hexadecimal code, to see. And here it is. 0, 1, 2, 3 up to 9 is identical to the decimal code. But you can display on one digit only something in the hexadecimal code, and that something is going to be in the form of letters. The mathematicians and engineers, they didn't want to invent new symbols for that mathematical base, and they used the letters A, B, C, D, E, F. No letters bigger than F, okay? So 0, 1, 2, 3, 9, A, B, C, D, E, F, okay? And this is gonna be the hexadecimal code. Now, the meaning of the hexadecimal code and all the calculation, I won't do it today because it's right before the end of the year. I don't want to complicate our life with that. We're gonna do this in January. Now, here is the point. I'm saying that these three displays, they show different things. This one here, it only shows the BCD code. The BCD code meaning whatever I'm counting, in the moment I'm going over 9, the display remains blank. Up to 15, and then restarts from 0. This one, it displays something after 9. But you have to recognize these particular shapes, because on one display, it's not possible to put the number 10, and this is 10. How do we know it is 10? Because the 1010 in binary. So on this one here, that's an intelligence, let's call it an intelligent display, is a kind of alphanumerical one, where there is a very special decoder located right here in this little square inside. So it's a package made by Texas Instrument. You can find it in two versions. The TIL 311, the TIL 311 cannot be found anymore, it's very rare. But instead you can find the DIS 1417. And what's interesting about this is that here where I put my pen, it's exactly the decoder inside the digit. So the decoder and the digit are in the same package. And this one displays the full hexadecimal code. So now we have B, which is 101111. This is C, which is 110012. This is D for 13, 1101. This is E for 14, 1110. And finally, when all the lights are on, this is 4 ones. And this is representing number 15, which is F. And for the decoder 48, this is a blank display. Okay, so this is a full hexadecimal display where it displays clearly in letters A, B, C, D, E, F. And this is the 7440A decoder. And now you can understand the difference between the three kind of displays, because it doesn't matter the displays, what matters are the decoders. Here we have a BCD decoder inside. Here we have a hexadecimal decoder, but is not capable to display the actual letters, this one. It only displays some symbols. And this is a full hexadecimal display where all the letters A, B, C, D, E, F are going to be shown uppercase, okay? So what is the relationship between the three codes, BCD, binary, and hexadecimal? If we take a look on the table here, all these codes are made of zeros and ones. So even these ones expressed by letters A, B, C, D, E, F, if you take a look at the binary, each of them is expressed in 4 bits as binary codes. But the decoder converts that particular code, let's say 1011, which is 11, it converts it in the letter B, okay? So this is the job of the decoder, not the job of the digit itself. This is why we have different kinds of decoders depending on the use. And of course, there are other codes using zeros and ones, like for instance, the gray code, which is used for motor moves and encoders, and not only the gray codes, but other kind of counters, like the Johnson's counter, where the combinations here may be different. All of them are made of ones and zeros, and the only code which is recognized as being the original or the standard or the pure binary is this one, where you have exactly these particular combinations, okay, from 0000 to 1111. All the other codes, they require, in order to be displayed, different kind of decoders, okay? So we identified the problem today what can we make the distinction between the binary, the BCD, and the hexadecimal code, and the actual mathematical calculation behind all that, and building a bigger counter, being able to use 2 displays instead of 1, this is going to be for the next time. Thank you very much for watching. See you next time. Bye-bye.